Hi, I'm Neha Das. In this video, I will be presenting the joint work with my co-authors on model-based inverse reinforcement learning from visual demonstrations. Teaching a robot complex manipulation skills from scratch can be very challenging. In such cases, learning from demos has several benefits. Amongst others, demonstrations can help bootstrap the learning of a suitable control policy. Further, in cases where it is hard to hand design a good cost function, demonstrations can be utilized to learn a suitable cost function as well. In fact, learning from demonstrations is quite intuitive, considering that this is one of the major ways through which humans themselves learn. In this work, we focus on learning good cost functions given task demonstrations. This is often termed as inverse reinforcement learning. Due to its potential for generalization and sample efficiency, we take a look at model-based IRL methods. There remain several challenges for this. Previous works have often required that demonstrations couple both action and state measurements, making them more costly to acquire. Most prior works also assume the availability of a transition model, which is usually not feasible in the real world. Finally, in previous approaches, learning a cost function required interleaving optimization for cost function parameters and policy parameters based on the current cost function without providing an explicit connection between the two. This may lead to instabilities in cost function learning. Our work addresses all these challenges. For learning appropriate costs, we rely on visual data from demonstrations by learning to detect key points corresponding to the manipulated object. We also learn a differentiable model of dynamics. And finally, we establish a gradient based connection between the interleaving steps in the cost function learning process, making it much more stable. We elaborate on this in later slides. Next, we give an overview of our system. As mentioned, we want to learn manipulation from visual demos. Our pipeline for solving this process has two steps. One, learn a cost function from the visual demo. And two, reproduce the demonstrated behavior by optimizing actions with respect to the learned cost. We first examine the second part of this pipeline, that is the visual MVC framework. This framework stitches together several components. These include a key point detector that detects pixel positions roughly corresponding to the object in the initial image, a dynamics model that predicts the key points and joint state at the next time step, and finally, the action optimization step. Minimizing this cost function with respect to actions via gradient descent gives the optimal set of actions that move the object to its goal position. We next provide an overview of learning the cost function. Our framework for learning the cost function builds upon recent work on gradient-based bi-level optimization. The inner loop of this framework optimizes the action trajectory using the current cost function parameters, while the outer loop updates the cost function parameters psi. In comparison to other IRL algorithms, our outer loop updates the cost function parameters by differentiating through the inner loop. The gradient-based connection between the inner and outer loops leads to a more stable and effective optimization. We compare results on learning from visual demonstrations on different cost function parameterizations. These include the weighted cost, the time-dependent cost, and the RBF weighted cost. We compare these to a baseline cost that measures the Euclidean distance between the predicted trajectory and the goal key points. We evaluate our methods on a placing task. Our demonstration for the task consists of a video in which the user moves the object first horizontally and then vertically to place it on the shelf. We evaluate all our learned cost function parameterizations and the default cost baseline on two different test cases with two different initial robot configurations. The best performing cost parameterization for test case 1 is the RBF cost, with the time-dependent cost being a close contender. We note that the weighted cost is unable to place the object fully on the shelf, indicating that the time dependency component in the learned costs plays some role in ensuring generalization. The default cost results in the object somewhat colliding with the edge of the shelf in an attempt to take the shortest path to the goal. This is in contrast to the learned costs, which presumably take cues from the demonstration. All the learned costs perform similarly and much better than the default cost for test case 2. More details and analysis on this work can be found in our paper. Thank you for your attention.